This video talks about two important concepts when it comes to the weather: humidity and dew point temperature. These are concepts that aren't frequently discussed by people who are talking about the weather. They usually talk about temperature and maybe wind, but humidity and dew point are really important things when it comes to understanding the weather. Here's a picture of what's called contrails behind an airplane. What are they? By the time you're done with this video, you should be able to explain them based on humidity and dew point. In the METEO video 5B.1, I told you about these 4 upcoming videos, and you've hopefully already watched 5B.2. This video replaces the one that I had originally intended, 5B.3, because this one definitely goes through more information than I want you guys to understand, and this video that I'm making right now really emphasizes the key points. Just a reminder, this particular video covers the describing of temperature-dependent capacity of air to hold water vapor, and it includes the concepts of relative humidity and dew point. Also, to remind you where we are in terms of meteorology in general, you've learned a little bit about the phases of water and latent heat, as well as processes that make the air rise, and now we're going to talk about humidity and dew point. So what is humidity? It's the amount of water vapor in the air. And remember, water vapor is gas, it's invisible, but we can measure it. We talk about air that is saturated as air that cannot hold any more water vapor. Why is this important? Well, once air is saturated, then it's probably going to form clouds and possibly rain. So we often want to know, how close are we to having saturated air? Now, the concept of saturation might be a little difficult to picture, but think about a sponge. A sponge that's dry has no water in it and it's unsaturated. If I take a sponge and I put water into it to the point where the sponge cannot hold any more water, if I put any more water in that sponge, it would just leak out, then that sponge would be saturated. So saturated air is sort of like a sponge that can't hold any more water. How do we measure humidity? Well, we need to give a quantity of water vapor in a quantity of air. So for example, we might say there are 5 grams of water vapor in 1 kilogram of air. To use the sponge analogy, we might say that there are 2 teaspoons of water in a sponge. So this is not very useful when it comes to how close are we to saturated air. Are we going to rain soon? Are we going to have clouds? Or is this very dry? So instead of humidity, we use the concept of relative humidity. How much water vapor is in the air compared to how much you could possibly hold, compared to saturated air. And we express this as a percent. So sticking with our sponge analogy, here's a sponge that is holding 25 grams of water, and I've determined that this sponge can hold a maximum of 50 grams of water. It's holding 25, and that's holding 50% of what it could. If I have a sponge that has all the water in it that it possibly could hold, let's say, for example, this one has 50 grams, then the sponge is saturated. It has 100% relative humidity. So saturated air has 100% relative humidity, just like the sponge. So this looks a little bit busy, but let me walk you through ways that relative humidity can change. So in this first diagram here, we have a flask that is sealed off from the atmosphere. We have a thermometer in to tell us its temperature. We have some water on the bottom, and then we have a whole volume of air that is 1 kilogram. And within that, we have 5 grams of water vapor. Again, we wouldn't be able to see that, but this is just something that was measured. This piece right here would always be information that would be given to you. How much water vapor can a kilogram of air hold? And in this particular example, for all 3 of these, we have 25 degrees centigrade, and that's going to change in the next example I show you. But for now, we're sticking with 25 degrees. So I would give you this information. So you are told you can have 20 grams of water vapor in this kilogram of air, but we only have 5. So if we have 5, We could hold 20. We have 5 over 20 or 25% relative humidity in this flask. Now over here, we've had some evaporation occur, and we now have 10 grams of water vapor in the flask. We still could hold 20, so now we have 10 out of 20, or 50% relative humidity. So by evaporation, we've raised the relative humidity. We continue this idea. Here we have 20 grams of water vapor. The maximum that it could hold is 20 grams, so 20 over 20 is 100%. So we have saturated air over here. So relative humidity can be changed in two different ways, and I just showed you one. We can either add moisture and raise the relative humidity, for example, from 50% to 70%, or we could remove moisture, which is not what I just showed you in that experiment, and that would lower the relative humidity. So one way to add moisture is evaporation, as we were just looking at. How do we remove moisture from the air? Well, very often here in Pasadena, we have these very dry winds called the Santa Ana winds, and those come in and they take moisture right out of the air, and so that lowers the relative humidity. The second way to change relative humidity is more common and more significant when it comes to the weather, and that is by changing the temperature. The amount of water vapor that air can hold is temperature dependent. Warm air can hold a lot more water vapor than cold air. So let's look at this experiment again. Now this time, you'll notice we have some different temperatures in each of these examples. We're going to be lowering the temperature and see what happens. So we start with our initial conditions. We have 20-degree air, which we're told can hold 14 grams of H2O vapor, and we have 7 grams of water vapor in there, so 7 out of 14 is 50%. So we have 50% relative humidity in this flask. Now we're going to cool the flask. Notice there's no water in here to evaporate or anything. The 7 grams is going to stay the same, but we're going to cool it. And now at 10 degrees, we learned that the air can only hold 7 grams of water vapor. So we have 7 grams, we can hold 7 grams, so we now have 100% relative humidity in this jar. This air is saturated. What happens if we go even colder? Well, over here at 0 degrees, it can only hold 3.5 grams. So what happens is the water condenses. Here it's water vapor, then it condenses to be liquid. Remember, condensation is gas to liquid. We get 3.5 grams of liquid, 3.5 grams of water vapor remain behind. We still have 100% relative humidity. So basically it rained in this jar because we lowered the temperature. So changing the air temperature can change the relative humidity. If we lower the temperature, it'll raise the relative humidity, for example, from 50 to 75%. If we raise the temperature, then the relative humidity might drop from 50% to 25%. This is very clear if you look at temperature variations throughout a 24-hour time period and the relative humidity. So this graph is showing a day here from midnight, 6 a.m., noon, 6 p.m., midnight, and the temperature throughout that day. And as you might imagine, it's coldest right before the sun comes up, then it warms up during the day and it gets cold again. The relative humidity is shown with this scale here, and in the cold part of the day, in the cold morning before the sun comes up, our relative humidity is about 70% in this example. Notice what happens as the temperature gets warmer. The relative humidity goes down because warm air can hold more water vapor than cold air. And so this is an example where we're not bringing in water vapor or removing it, we're just changing the temperature. So this is a mirror image of the temperature. And if you understand this diagram, then you really understand this concept. So the dew point temperature is the temperature at which air would need to be cooled to reach saturation. So for example, if it's 65 degrees out and the dew point temperature is 60 degrees, then if it cools another 5 degrees, we're going to have saturated air. And the key is cooled. The air will always be cooled to the dew point temperature. So in the morning, you might sometimes see dew on the grass or your car, but it didn't rain overnight. And that's because during the evening, the temperature dropped below the dew point temperature. If I go back to this picture, what that means is in the evening, it got cold enough that this relative humidity went up to 100%, which is not on this scale, but that's what that means. Air cooled below the dew point temperature causes condensation, and remember that is the gas going to a liquid. You can get dew, such as on this spider web. You can get fog or clouds. The key here, though, is that water vapor can't just condense onto thin air. It has to condense onto something. So here it's condensing onto the web. The previous slide showed you how it was condensing onto grass or a car. What's going on here with the fog and the clouds? Well, it's actually condensing onto little itty-bitty tiny things called condensation nuclei. Oh, I forgot. I like this picture because look at this little sign, fog. What else could you possibly put on that little picture? Condensation nuclei are little tiny bits of dust or ash or salt from the ocean that are in the air, and they're very tiny, but those are enough for water vapor to condense to a liquid form. And I like this picture because it shows you how tiny we're talking about. Here's a typical raindrop. Here are cloud droplets and fog droplets that are much, much tinier than the raindrop, and that's why they don't feel like rain. And then the condensation nuclei are even tinier. So what is going on here? See how well you understand these concepts. Put this on pause for a moment and see if you can figure out what is happening on the outside of this glass. Well, first of all, there's clearly some water condensing onto the outside of the glass. There's liquid water. And that's because the glass is cold from the ice. And it's so cold that the surface of the glass is below the dew point temperature. Let's say the dew point temperature is 60 degrees and the ambient temperature is 80 degrees. And of course the glass is getting down well below 60 degrees. So water vapor from the surrounding air condenses onto that surface. And that's an important part of this picture, is that the water vapor that's condensing on the glass is not coming from inside the glass. It's coming from the air around the glass. Now, sometimes people describe this phenomenon as sweating. They say the glass is sweating. And that might make you think, well, the water's coming from inside and going through the glass, just like when people sweat, it comes from inside the body. So that's kind of a misnomer to say that it's sweating. All right, finally, the contrails. Contrail stands for condensation trail, so you probably have an idea of what's going on here. The key is what's coming out of that engine. Among other things, there's soot, which is basically dirt, particles, pollution, and water vapor. And so as that soot comes out, it's basically providing condensation nuclei, and the water vapor comes out, and it's so cold that the water vapor condenses and often generally freezes, so it doesn't just go from gas to liquid, but it goes all the way liquid to solid. And then we get these clouds, if you want to call them that are condensed water vapor from being below the temperature of the dew point.